Well, good morning, and thank you all for the honor of synthesizing a bit more about this global energy revolution that's rapidly taking us towards a cheaper, resilient, and carbon-neutral future. And the overarching story here is a rapid and irreversible global shift from fossil fuels to renewables, fuels to electricity, inefficient to efficient use, and centralized to distributed supply. But the transition from inefficient to efficient use is not a binary are you efficient or not? It's a spectrum, and it keeps evolving rapidly. Now, together, efficient use, renewable supply, and electrification of heat and mobility are squeezing out fossil fuels from both sides. Their large fraction of global energy today is as misleading a guide to their future as was the number of horses in 1900, just before cars displaced them. In the United States, every energy-using sector has already passed peak fossil fuel, and the world's total use of fossil fuels, shown here, peaked about 5 years ago and began bumping along a plateau with minor excursions both ways due to weather or war. But right around now, led by renewable electricity and electric vehicles, carbon-free power is starting to meet all demand growth, then more, tipping fossil fuels into permanent and steepening decline. The light gray and dark gray scenarios shown at the far right there are from Bloomberg New Energy Finance, but they're similarly framed by the International Energy Agency, BP, Shell, McKinsey, Rystad, and others. And the more efficiency shrinks demand, the faster the now exponential growth of renewables will displace fossil fuels. In the past 48 years, in the United States, for example, saved energy, about 2/3 due to smarter technologies, has dropped primary energy use by 64%, with huge cumulative savings. Renewables, meanwhile, nearly trebled, but with 26 times less cumulative impact. Who knew? Renewables get virtually all the headlines because they're visible on the skyline, on the rooftop, whilst energy is invisible and the energy you don't use is almost unimaginable. And yet saved energy is half of the world's historic decarbonization and at least half of the world's future decarbonization. A little more history. Around 1975, US government and industry all said that the primary energy intensity, that is the total input energy needed to make $1 of GDP, could never drop. A year later, I heretically suggested it could drop 72% over the next 50 years. So far, as I mentioned, it's just dropped 64% in 48 years. And yet the innovations already added by 2010 can save another threefold, twice what I originally thought, and at 1/3 the real cost. And today that looks conservative because optimizing buildings, vehicles, and industry as whole systems, not as piles of little parts, can often make very big energy savings cost less than small or no savings, turning diminishing returns into increasing returns. Vigorously applied, such integrative design could quintuple energy productivity worldwide by about 2060, or treble it by about 2040, as documented in this foundational paper. I'll give you examples shortly, but this is only end-use efficiency, the services per unit of final energy delivered to the user. It doesn't include the 2- or 3-fold upstream savings from electrification with primary renewables. Here's how that goes. 3 columns starting on the left illustrate that upstream or supply-side shift. At the upper left, the huge conversion losses in red from thermal power stations are eliminated at the lower left when solar and wind power in green generate directly without a steam cycle. In the middle column, fuel combustion at the top provides heat several-fold less efficiently than a renewably powered heat pump concentrating free low-temperature heat from the environment. And in the right column, petrol and diesel engines with their big losses in red are far less efficient than renewably powered electric motors in battery electric vehicles. So the systems across the lower row replacing fossil fuels with renewable electricity are several-fold more efficient in turning renewable electricity into delivered services. But note, this does not yet include higher efficiency in the equipment being powered, or the building or material being heated, or the vehicle being moved. That's the end-use efficiency bit, and doing that first makes the heat pumps and the EV batteries smaller, cheaper, less mineral intensive, and both these kinds of efficiency multiply to form primary energy efficiency. The supply side savings here of about 2 or 3-fold avoid nearly $5 trillion of global waste each year. That's almost 5% of world GDP. And yet they're only half as important as the largely overlooked gains in end-use efficiency that I'll illustrate next. Now, the world just agreed in Glasgow to double the speed of saving energy overall, and that's before including integrative design. But integrative design can make the end-use efficiency resource several-fold bigger and cost less because it uses not more but fewer devices and not fancier but simpler devices, more artfully chosen, combined, timed, and sequenced. We're familiar with resources like copper ore bodies or oil reservoirs, finite and depletable assemblages of atoms. In contrast, energy efficiency resources are infinitely expandable assemblages of ideas, depleting only stupidity, a very abundant resource. A few examples. My wife Judy and I live 2,200 meters above sea level in the Rocky Mountains near Aspen, where temperatures used to dip to minus 44 Celsius. The central atrium that the building wraps around, seen here in a February snowstorm, has so far produced 81 passive solar banana crops. Someone said I had really big earphones. And it was cheaper to build this way 42 years ago because leaving out the heating system subtracted more construction cost than the super efficiency added to get rid of the heating system. Our house helped inspire several 100,000 European passive buildings with no heating and roughly normal construction cost. And it doesn't have to look like this to work like this. A Bangkok analog saved 90% of the air conditioning energy with better comfort and normal construction cost. And nearly everyone on Earth, certainly everyone in Australia, lives in a climate somewhere between those of Bangkok and Old Snowmass. But wherever you live, integrative design gives many benefits from each expenditure. So the white arch at the top of the upper middle photo has 12 different functions, but it has only one cost. In 2010, integrative design let our Empire State Building retrofit save 38, later 43% of its energy with a 3-year payback. Then the owner wanted to redouble the savings to 80%. So I'll compare the before and after intensities in green and give you the percentage savings in yellow. Now, 3 years later, our cost-effective retrofit saved 70%, making this difficult half-century-old federal complex more efficient than what was then the best new U.S. office, which in turn is only a third as efficient as RMI's net positive, no mechanicals passive office near my home, now using about a ninth the normal amount of energy in the coldest North American climate zone, and producing, of course, more energy than it uses. This Bavarian building uses 2/5 less energy still. And yet, all these technologies existed more than a decade ago. What's mainly improved is not so much technology as design, how we put the bits together. And it keeps improving. The Dutch Energiesprong method of super outsolation can profitably retrofit most buildings to net zero efficiency, and installation can take as little as a day. Even in tropical climates, traditional passive building design can keep you feeling about 16 to 19 Celsius cooler, while redesigning big mechanical space cooling systems can at least treble their efficiency, all with excellent economics. In fact, now that's more like quintuple. RMI's Global Cooling Prize just quintupled air conditioner efficiency, now heading to market. But an experiment 5 years ago revealed a startling alternative. It turns out that purely radiative cooling kept people comfortable outdoors in Singapore without moving, drying, or cooling the air. Instead, in a shaded but open-ended pavilion, about 10 square meters, people stayed cool just by radiating their bodies' far infrared rays into panels circulating slightly cooled water and shielded from the humid air by an air-gap plastic film. Radiant temperatures of 23 to 25 degrees could deliver comfort in air up to at least 32 degrees at 80% relative humidity. And such mild cooling, just 7 to 9 degrees below ambient, can often be done passively with no electricity, potentially about eliminating the world's long-term growth in peak electricity demand. Inside buildings are other surprising opportunities. For example, this fist-size heat pump can deliver 6 to 15 units of hot water per unit of electricity versus the Australian norm of 3 or 4, whilst this electric conduction cooking system is 2 to 4.5 times more efficient than induction and otherwise superior. But smart technologies are less important than organizing them to do the right things in the right order. Let me illustrate this first for lighting, then for space cooling, then we'll get into industry. Most lighting retrofitters start by installing higher efficacy light sources, more lux per watt, and better controls. But the Illuminating Engineering Society's Handbook of Fundamentals rightly tells us first to improve the visual quality of the task, then the geometry and cavity reflectance of the space to bounce the light around better, then the lighting quality, cutting veiling reflections, that's good for about a factor 7 saving, a typical office, cutting discomfort glare from too bright luminances in your field of view. Then you optimize the amount of light on task, the illuminance, then you harvest and distribute the natural light, and only then do you optimize the luminaires and the controls and maintenance and training. This specific sequence can often save an order of magnitude more energy with better visual performance than aesthetics, and yet most retrofitters proceed in reverse order, worst buys first, so the luminaires don't become fewer and the illumination doesn't get better or prettier. The same is true for space cooling. You might wonder how RMI's office eliminates heating and cooling equipment from minus 38 to plus 37 Celsius. That's our design range. Well, decades ago, I once asked my hostess in Japan why she didn't heat her nearly uninsulated house, and she looked puzzled and very sensibly replied, "Why should I? Is the house cold?" People, you see, have nervous systems and comfort sensations, but buildings don't. So we should keep people comfortable, not buildings. Therefore, the Innovation Center of RMI delivers task comfort like task lighting. Each person has a hyperchair that delivers the desired real-time comfort from a few watts of silent fans and 14 watts of car seat heaters, all powered by a lithium battery, and those maintain ASHRAE comfort to the person sitting there in indoor air temperatures from 16 to 29 Celsius. Excellent ceiling fans further expand the summer comfort range by 5 to 7 degrees, not the normally assumed 3. Super windows that pass light and block heat slash the radiant loads and insulate like 14 sheets of glass. We recover 93% of the ventilation heat or coolth. The building's super insulated, nearly twice as airtight as a passive house, and passively cooled by active exterior shading and natural ventilation, including automated night flush to cool phase change walls. And therefore, we don't need other passive options, nor active non-refrigerative cooling that can yield over 100 units of cooling per unit of electricity, nor do we need refrigerative cooling, nor do we need fancy storage and controls. And even in the most severe climates, this whole system approach can save 90 to 100% of the cooling energy with better comfort, lower capex, and higher uptime without reaching step 5 or usually even step 4. And yet again, most practitioners pursue these options in reverse order, worst buys first. Well, my team's 2011 business and design synthesis, Reinventing Fire, informed by hundreds of such cases, showed how in the United States by 2050, at historically reasonable speed, buildings could become 3 or 4 times more efficient, saving $1.4 trillion net present value with an average 33% internal rate of return. So the savings are worth 4 times their cost. And we also showed how industry can double its energy productivity with an average 21% IRR. Industry uses half the world's energy and electricity and emits about 1/3 of all greenhouse gases. Now, in recent decades, RMI's latest $60+ billion worth of industrial redesigns typically found about 30 to 60% energy savings on retrofit across a range of industries. This paid back in a few years, and it far outperformed the orange oval zone in the upper left, where most energy service companies deliver disintegrated design. In new projects, integrative design generally yielded 40 to 90+% energy savings with lower than normal capital cost. And in both cases, you see the range of industries is quite diverse. Our challenge was often to understate the likely savings by enough that the client might believe us. Now, these results are not magic. They just come from systematically applying integrative design using orthodox engineering principles, but asking different design questions in a different order. After capturing big system boundary opportunities to eliminate waste, what's left is a technical production system, and within that narrower boundary, if we leave aside all the downstream savings and for now focus just on producing materials and products that are really needed and are optimally chosen and designed, then there are 8 familiar places to look for big savings, aside from those too obvious to mention, like turning off kit you're not using. Most industrial engineers focus largely on the second item, thermal savings and integration, get very good at it. And after brief comments on process heat, I'm going to illustrate the power of digging into the 4th and 5th terms, fluid handling and drive systems. But the other 5 have powerful stories as well. Now, of the final energy going to global industry, about 70% makes process heat, 90% of it fossil fueled. Therefore, nearly 2/3 of industry's final energy use, or 1/3 of the world's final energy use, is fossil fueled process heat. And half of that is needed at under 400 Celsius degrees, and nearly 1/3, the 2 green wedges, is needed at under 100 degrees. We boil water into steam by burning fuels, not because boiling needs combustion, but because it's what our ancestors did. We make steel and cement in ways designed to use combustion temperatures because fossil fuels were handy, but they burn at upwards of 2,000 degrees, a huge mismatch. Now, modern industrial heat pipes that John mentioned can concentrate waste heat or free environmental heat to deliver several-fold more heat at upwards of 180 Celsius now, but better still is not to need the heat. So when J.B. Straubel was designing Tesla's all-electric, all-photovoltaic-powered battery gigafactory in Nevada, his first design decision was to have no gas pipe and do no combustion. This saved a precious 6 to 12 months on the air permit. What's that worth in the battery business? He got his permit in a half hour because he's not burning anything. And then he started looking at the process heat. And they ended up finding the biggest use was continuously redistilling a solvent, which would normally be done with 1 thermal megawatt of gas boilers. But instead, he replaced it with a single 15 kilowatt electric heat pump that would fit under this lectern, because the process needed only a 1.5 Kelvin change in temperature. So he must have been very near the Carnot limit. That physics-smart choice saved 98.5% of the energy and all of the emissions. And then the rest of the process heat was pretty much the same story. The European factories retrofit by Crowley Carbon similarly saved 92% of the process heat energy. So before you just replace a furnace or boiler with a heat pump, carefully consider how much heat and how hot you really need. And if it must indeed be really hot, then solar process steam technologies like Glasspoint, soon to be mass-produced with Saudi government investment, can deliver 500 Celsius steam. Each module puts out about 5,000 tons a day. And at least 2 solar firms are offering 1,000 degree solar process heat. But whoa, before we rush to substitute renewable for fossil fuel supply, what should we do first? Start with demand. Need less, use other, use less, use longer, use again, align incentives. Only after minimizing need should we redesign the process to use less process heat and cooler and cleaner. Now, there are some big menus here. The many other diverse demand-side options for using less material multiply to very large savings before we get to circular economy and more benign products and more efficient processes and fuel switching and renewables. Such efficient end use has big multipliers back upstream to extraction and production, leaving far less high-temperature process heat to decarbonize. So adding the missing first 8 lines to the conventional 12-line opportunity space that is greatly expanding the system boundary makes the problem a lot easier. And if you take this menu seriously, you'll learn how to do almost everything with almost nothing. rethinking the purpose of a process before you focus on the technology can be powerful. Let me give you a sweet example. A new environmental manager at the U.S. supermarket chain Safeway was asked to figure out what to do with the fatty acid or fatty waste left over from using high-pressure water full of nasty chemicals to clean out the pipes in the ice cream factory after making one flavor so they can set up for the next batch in a different flavor. The cleaning and disposal were very expensive. And one day the manager asked, why are we throwing out all this tastely and costly material? Why don't we just run the differently flavored batches continuously back to back, keep track of the mix zone where the flavors are blending, and package and sell it as, I don't know, magical mystery tour ice cream, exotic mixed flavors, no two alike, you'll love the exciting variety. Well, it was a huge hit. The profit margin was enhanced by saved raw materials like cream and flavorings, avoided cost for the waste disposal and time and materials for the cleanouts that weren't really needed for hygiene, the extra production achieved for free by converting cleaning capacity and time into more production, and most fun, the extra profit margin when they discovered that instead of having to discount this non-standard product, they could actually charge a novelty premium. Of course, the new product cannibalized sales of old products, but one hopes those were sold by competitors who didn't think of this first. Yum. So this delicious example illustrates the logo in the lower right corner, the Japanese phrase muda nashi, no muda. Muda is the Japanese term for waste or purposelessness for any measurable input that doesn't produce customer value. So no muda systematically turns every kind of waste into value and profit. And there's Mura and Muri, and Toyota production system gets complicated. Another tasty example. RMI was once helping to redesign a private firm that is the world's largest grower of apples and maker of cider. And here are three of our most memorable findings. First, that the apple seed coat being discarded with the rest of the apple core contained very powerful antioxidants that were worth more than all the rest of the apple. Nature's good at protecting seeds. Then we found the orchard trimmings that the firm was paying to dispose of would make a wonderful substrate for growing shiitake and Ganoderma mushrooms that were worth a lot more than the cider. And then the whole value chain had been spoiled by using the wrong metric. This was discovered by the modern languages graduate who married the chairman's daughter and could have had any job he wanted, but he chose to start as a manual laborer in the orchards for 2 years. So after that, he was the only executive who understood the firm's production process end to end. The rest were good at finance and marketing, but they didn't like getting their hands dirty, let alone blistered. So what he found was a metric error so simple nobody had noticed it, but so powerful it redesigned the whole enterprise. You see, making cider requires sugar, tannin, and flavorings. Apple trees like to grow up tall and concentrate these products in small, sweet apples high up because it takes osmotic energy to lift up water. But the orchardists were being paid by the ton. So they trimmed the trees to bush out low so they could be easily harvested with shakers like almond trees. This yielded more tons of what? Of big watery apples. So you had to boil away, it was cheaper to harvest, but then you had to boil away the extra water to get the desired products. And a lot of apples fell on the ground and got bruised and dirty, more tons of mush and mud, adding wild yeast strains that spoiled the carefully controlled fermentation. So the firm began paying not for tons, but the ingredients that the process required, and then turning the various wastes into value, and the results were really juicy. In short, breakthrough industrial efficiency starts with why and what questions before it gets to how. Asking the right questions in the right order often eliminates unneeded tasks, steps, processes, equipment, and inputs before improving the remaining ones, and then this has many knock-on benefits. So let me now offer you a few other quite concrete examples. Let's start with fluid handling. Half the world's electricity runs motors. Half the motor torque turns pumps and fans. Well, just better pipe and duct design can save 80 to 90+% of the friction, and therefore of the pumping power and energy. In our house, 97%. And if everybody did this, it could save roughly half the world's coal-fired electricity, or a fifth of all electricity, with paybacks typically under a year in retrofit and instant in new build. But this isn't yet in any standard engineering textbook, official study, industry forecast, or climate model. Why not? Because it's not a technology, it's a design method, and few people yet think of design as a path to speed and scale. And yet it can be very important. In the 24-story Hyatt Hotel in Buggy, Singapore, Liang Glock retrofitted a 92% in the electricity used to move air and water. No magic, just beginner's mind, careful measurement, good whole system engineering. Pity they wouldn't let him retrofit the whole building. Now, pumping is the biggest fluid handling task, and normally a critical pump with an in-place spare pump would be laid out like this, so the flow always go through 2 right-angle bends, friction. So why not lay it out like this so the main flow has no bends and also fewer valves? The same logic applies with identical pumps in tandem, a very common arrangement. So to wring out the friction that wastes about 15% of US electricity, we simply use big pipes and small pumps, not small pipes and big pumps. And notice we've raised up that little blue pump to meet the pipe rather than dipping the pipe down to meet a pump on the floor and then back up again. There go 4 elbows. And to get rid of the remaining elbows and their friction, we lay out the pipes first, then the equipment, not the other way around. So the 10 chillers that used to be in a neat row get staggered until the elbows go away. We lay out supply pipes as if they were drains. We bend minds, not pipes. And thus our colleague Peter Rumsey's retrofit of the Oakland Museum's condenser water pumping loop cut out the pumping energy cut it by 3/4 with a 2 or 3 month payback, a retrofit. And it eliminated 15 pumps that will never again waste energy and maintenance costs. I love negapumps. And then repiping the chilled water loop and adding variable frequency drives doubled the flow and saved 85% of the energy. Here's how we normally lay out in big buildings the piping of cooling tower water back to the chiller's condenser. But if we lay it out instead the way Rumsey does, everything gets better. Why don't we all do this? Just force of habit, bad habit. Now think of the whole power and pumping system. From the fuel burnt in the thermal power plant to the end use, many successive losses compound. So only 1/10 of the energy in the fuel comes out the pipe as flow. But now turn those compounding losses around backwards from right to left and they become compounding savings. Every unit of flow or friction you save in the pipe saves 10 units of fuel cost, emissions, and global weirding at the power plant. And as you go back upstream, the components get smaller and cheaper, so the total capital cost goes down. And then once your pump or fan needs 5 or 10 times less torque, you can replace the big inefficient motor system with a new right-sized super efficient one and save around half the remaining energy by 35 integrated component improvements, 28 of which are free byproducts of the first 7. So that's about twice the saving you would normally get from the usual 2 or 3 disintegrated improvements and at 1/5 the unit cost. That raises the potential savings in fluid handling systems from 1/5 to 1/3 of global electricity use. That's an awful lot to be missing from climate models and utility demand forecasts. Now let's apply the same logic to big old data centers. It came up earlier. 2/3 of the fuel fed into the thermal power plant is lost in the plant and grid. Half the metered electricity is lost in the cooling system and the uninterruptible power supplies before it gets to the servers. Half the server energy doesn't reach the chips because it's lost in inefficient, usually very underloaded power supplies and many superfluous fans. Next comes severe underutilization of computing resources, partly through insufficient virtualization. The resulting energy flow, little tiny yellow stalk down there, is about to vanish, so let's magnify it. Next comes bloatware, running many unnecessary threads and processes, and making simple tasks very complex because compute cycles were cheaper than programmers' attention and someone else bought the electricity. Downstream of all that, you may even have inefficient business processes. In all, the red numbers at the bottom reveal that just a few 100,000ths of the original fuel energy actually delivers customer value. Where should we start fixing this? As always, downstream. Start at the end. First, write elegantly terse code optimally complied with the goal that every compute cycle is a needed and wanted one. I thought this could save an order of magnitude in compute cycles, but recent tests suggest it's actually 2 orders of magnitude. And the shift to mobile devices makes efficient code valuably stretch battery life. Well, then you can at least quadruple, nowadays more, the server's efficiency, and they will need a lot less cooling and power supply, both of which can be done in smarter ways. And then we could even save half the utility losses with fuel cell trigeneration, cheaper than the UPSs it displaces. Well, if you multiply these savings from downstream to upstream, you cut energy use by at least 2 orders of magnitude. In the project for which we made this diagram in 2009, the client rejected most of our recommendations, so we were only able to treble efficiency at the same CapEx. And we hardly ever do that badly. But our partner EDS said that had they all been adopted, we'd have saved about 95% of the energy and half the total CapEx. Well, in 1989, my team synthesized how to save nearly half of US drive power with retrofit paybacks under a year at a 5 US cent tariff. And I suspect the potential savings may have got bigger and cheaper by at least as much as they've been used up. This is, by the way, twice the IEA's estimate, because they count a few improvements and we count 35. Let me just give you a few highlights of that. One of our more surprising findings was that although asynchronous motors generally use more and better copper and iron to get their higher efficiency, so they should cost more to make, for some reason they're not priced that way. And when we last requeried the US Department of Energy's free Motor Master Plus database, 2 generations of standards had already knocked the worst motors off the market, but there was still no correlation between efficiency and price for common motor types up to at least 220 kilowatts. So around 1998, you could buy the most efficient 100 horsepower asynchronous motor, cheaper than nearly the least efficient ones with otherwise comparable specifications, and that would save you upwards of $20,000 US present value per motor. I suspect this is still true, and it's true of a lot of other things, common industrial pumps, most rooftop chillers, and a lot of other things. So don't assume that efficient kit must cost more. Shop around. Remember, in God we trust, all others bring data. And the most efficient motors now on or entering the world market have efficiencies equivalent to IE7 to IE9 if the standards actually went that far. And they needn't cost more because of the clever way some manufacturers are combining new designs like axial flux, new materials like amorphous iron, cheap ferrite magnets, and so on. And these things are starting to get to market. IE6 is on the market, IE7 is getting into the market, and it's going to get cheaper with emerging iron nitride supermagnets, cheaper than rare earths and potentially more powerful, or by saving copper and iron, like the new designer called Zeus Motor, whose permanent magnet IE7 equivalent designs are said to have 1/3 the normal mass. In fact, there's a new aviation motor from Denso and Honeywell with 100 continuous kilowatts from under 4 kilograms of motor. 25 kilowatts per kilogram. That's twice as good as the best automotive motor, 3 times the Tesla motor efficiency, 5 or 10 times most EV motors efficiency, or I shouldn't say efficiency, but power density. So that frugality of materials implies quite a modest cost. And there's a whole lot more such data where that came from. Another important opportunity is to right-size motors to their measured load, because part loading not only wastes capital, but can greatly reduce efficiency. For example, in a 7.5 kilowatt IE2 or 3 motor, the highest efficiency is limited to the small or medium-sized bullseye in the upper right corner of the motor map of torque versus speed. Look at the upper right map here. But this German line of reluctance motors offers high efficiency all the way down to about 20% load and at any speed. So the gold zone in the lower left map shows the energy savable at part load by running that 7.5 kilowatt model rather than a normal IE3 like the one in the middle map on the right. And the advantage captured by the gold zone can easily be an extra 10 or 20 percentage points beyond the roughly 5 points you'd expect from just going to an IE5 motor. Here's a graph showing the same issue over about a 500x range of motor size. I won't elaborate it here, but the point is that the more efficient your motor gets, the flatter an efficiency curve it's likely to have across load. And this is relevant if you have the same problem we do in the US, I suspect you may, namely that half of our industrial motors never exceed 60% of their rated load and a third never exceeds 50% of their rated load. So they're a lot less efficient than the full load nameplate rating says. And also, when you underload an asynchronous motor, it runs faster, so it wastes more energy in pumps and fans, which are cube law machines, by driving more flow than you need. Well, because of those two effects of pervasive oversizing, right-sized new motors will save more energy than expected, and they'll cost less because although price does not correlate with efficiency, it correlates very well with size. So you also then find the flatter efficiency curve across the load range improves flexibility. Premium motors typically have higher and flatter power factor that reduces distribution losses and capacity needs. They run cooler, so they have lower resistive loss. They have longer life because each 10 Kelvin of reduced temperature roughly doubles expected life. They have longer grease life, so you need to lubricate them less often and with less downtime. Now, even without most of the integrative design or many other innovations, my team's Reinventing Fire Synthesis found that U.S. electricity use could shrink by a quarter by 2050, assuming all electric autos and a 2.6-fold bigger GDP. This quadrupled electric end-use efficiency would save electricity for a tenth its U.S. retail price, so we should have bought a lot more efficiency than just a factor 4. And don't forget materials efficiency, explored in strong but scattered literature I synthesized a few years ago for RMI and MIT Sloan Management Review. Notably, smarter structural design and new business models can profitably save at least half the world's cement and steel that now release about 15% of global CO2. Of course, you can also better spec the mix of the concrete and not slop it around the job site, save another factor 2. But let's just focus on the factor 2 from better structural design with a few examples. Substituting tension for compression structures typically looks better, costs less, and uses about 1/8 the tons. Pouring concrete into curvy fabric forms, not rigid prismatic forms, can often save over half the concrete by putting strength and stiffness only where you need them, and then the weight savings compound because you need less strength to hold up less weight. An airy 3D printed bridge can carry mainly its users, whilst massive concrete bridges support mainly their own weight. Here's a stainless steel 3D printed bridge. And most importantly, floor slabs like this are about half the total weight of a typical mid or high-rise building. And a 5 centimeter thick folded concrete floor slab, or a shallow vaulted dome, can replace a 30 centimeter thick flat slab and cost less and save 3/4 of the cement and save all of the steel. Carbon fiber rovings turn out to be cheaper in that application. Well, once you've got thin floor slabs, you can combine with passive energy design to save another 15% of core structural materials and about 3/4 of the energy in a new mid or high-rise building like the Singapore one at the upper right, whilst increasing net rentable space by a stunning 55%. How do you do that? Well, you design out the vertical meter of mechanical plenum at each story that you see at the far left, and then within slabs, you can fit 3 stories with unchanged 2.8 meter ceiling height into the current height of 2 stories. Cost, complexity, and time fall dramatically. Why would you do it any other way once you see that? So how much electricity will the world need long term? Well, no one knows. The high standard projections risk major overbuilding and stranded assets, and that risk is rising with the obvious trends, plus some further innovation. For example, in 2021, efficient structural design emerged as an important way to save basic materials, as you just saw. In 2022, we gained low-temperature ways to make steel and cement, such as electrochemical iron making at 60 degrees, like a hot cup of coffee, not at 1600 degrees. That process is running today in a pilot plant of an Indian entrepreneur in Boulder, Colorado. In 2023, geological hydrogen became credible and may end up saving most or all of the planned green hydrogen and the green electricity to make it. These are some of the surprises coming at us that I mentioned on the panel. That's just 3 years worth. There's more coming. Lest light industry have all the fun, I want to end with a heavy industrial example, a multi-billion-dollar cryogenic plant in far northwest Australia turning methane gas into liquefied natural gas at minus 161 Celsius for marine shipment. This is in a blazing desert that was at 54 degrees the day we arrived. And we ended up finding ways to save over 40% of that plant's energy on retrofit with a few years payback, or in an expansion or new build, how to save upwards of 60% at lower capital cost. Now, saving energy is like eating an Atlantic lobster. There are these big obvious chunks of meat in the tail and the front claws, but there's a roughly equal quantity of tasty little morsels hidden in crevices that require some skill and persistence to recover. And of course, we need to go for the whole lobster. It's really tasty. Or to pick a different culinary metaphor, the Singaporean wizard Liang Lok, who is on our charrette team, says, like Chinese cooking, use everything, eat the feet. So let's go look for some juicy feet. Now, this diagram does not show the throughput of natural gas molecules that get liquefied for sale. Rather, it shows the fuel gas burnt to process that product. 73% of the fuel gas, which otherwise could be liquefied and sold, instead becomes 0.8 gigawatts of waste heat, typically at 420 to 540 Celsius. Throwing that heat away requires considerable energy and investment. So in this supposedly optimized process run by one of the world's top oil majors, only 19% of the fuel gas ended up making the main LNG product. Oops. Now, the big tail of this juicy lobster is actually the power plant, with simple cycle gas turbines run inefficiently and hence expensively. Saving a little electricity could shut down some of the turbines altogether, and to facilitate that, we could start adjusting operations for better load management, like making liquid nitrogen at night. When it's cooler, the turbines run better and the plant is drawing less power. And instead of running multiple turbines very inefficiently at part load, for redundancy and for instant handoff, we would use a naval technique we developed called virtual trail shafting to run fewer turbines at peak efficiency without losing reliability. The big front claws of this lobster came from the 3/4 of a gigawatt of heat that the operators were paying heavily to throw away at 400 or 500 plus Celsius. Now, some of that heat could directly replace furnaces and electric process heat that they were simultaneously operating. But we could do a lot more with it too. We could cascade through heat reuse to cool production, desalination, and even Rankine bottoming cycles to make more electricity. Brine from the desalination could be sold to the local salt works. How did they throw away that amount of very high temperature heat? Well, they had 700 fin fans spun by 15 megawatts of electricity. That was about 21 million Australian dollars worth of electricity in present value. And the fin fans could be run much better, but better to redesign them. So after minimizing the heat to be rejected, we would scrap the existing fin fans and put in redesigned ones, micron misted on the inlet, with very efficient motors and adjustable speed drives. and above all with aerodynamics much better than the standard antiques that they had, which were 1940s vintage. The new design would apply basic physics like this. They'd cost a little more, they'd work better for longer and pay back very quickly. Now, the efficiency lobster also has a lot of tasty little morsels you have to dig out. Some may be obvious, like capturing pressure letdowns and expansions, or painting cold stuff white when it's going to sit in the sun, or shifting heat between the parallel chiller trains to keep the whole plant tuned up as the winds shift. But the funniest discovery, the last item listed here, was the $1 billion we found lying on the ground. On arrival, as I was walking the site, I puzzled my host by keeping my weapon of choice, which is an infrared thermometer, pointed mainly at the ground. Well, that's because the ground was paved with black asphalt and dark gray concrete, and mounted above it were several hectares of plumbing they were trying to cool to negative 165 Celsius. So I figured that covering the ground with anything white and cheap, white sand, crushed limestone, oyster shells, whatever, could cool the site by about 10 or 20 Kelvin. And that evening we ran regressions on the plant's efficiency as a function of ambient temperature. Next morning we announced that whitening the ground would be worth about $1 billion present value. Oh, and then the pipes themselves were beautifully sheathed in shiny stainless steel, so I pointed the infrared thermometer at those. A little thought experiment. If you take 3 pieces of sheet stainless steel, one bare, one painted black, one painted white, and you put them in the sun, which will get hottest? Probably the bare one, because stainless steel has terrible infrared emissivity. I mean, even black paint might run cooler, but anyway, white paint costs the same. It's just physics. And then there was a nice lesson about starting all the way downstream. The next to last thing the LNG sees before it goes aboard the marine tanker is a big spherical tank where it sits for a few days. And that LNG in the tank must be continuously circulated, because if it stratifies, it could suddenly roll over and break the tank and maybe incinerate the whole multi-billion-dollar facility and anybody around for miles. So we found that the LNG was being circulated by an immersed motor pump system with a combined efficiency of 68%. But it'd be worth paying a lot for a high-temperature superconducting motor like the Navy uses that would run a good pump at a combined efficiency of 89%, reducing the product wasted by boil-off by 2/3 and leveraging all the savings back upstream to liquefy that gas. Well, then beyond that, the Australian naturalist and sea captain Jay Harmon developed a biomimetic rotor whose ring vortex can circulate 4 megaliters of water with just 24 watts, and that, or an aerator solution replacing 137 kilowatts with 0.56 kilowatts, could get us to 99% or so motor and pump efficiency. That's over 30 times less boil-off of precious product. Even those giant tanks had been painted dark green to make them look pretty. We suggested white. Well, anyway, what's the very last thing the LNG sees before it goes aboard the tanker? It's the pipe from the tank to the ship, including the loading arm. Well, surprise, in between cargoes, those components are not kept cold. So a lot of precious LNG never gets into the ship. It vaporizes first, trying to chill the pipe that's long been baking in the tropical sun. Nobody'd fix that because it wasn't part of the plant. It was some kind of miscellaneous dock kit. So think of the leverage from avoided LNG loss at the dock all the way back upstream through the whole plant. So you can imagine a kind of 5-layered wedding cake, to mix my culinary metaphors some more. Efficiency everywhere, combined cycle generators that run the chillers directly off the turbines, supplemented by variable speed motors, use waste heat from the turbines, ammonia absorption chillers chilling the process streams and perhaps the turbine inlet air, since aeroturbines are optimized for airplane cruise altitudes, not at sea level in a hot desert. Evaporatively cool the gas turbine inlets as well, eliminating their helper motors. Then off the bottom of the ammonia chillers, distill water for use and sale, along with salt and brine byproducts. Use the sweet water in very efficient cooling towers and to micromist inlet air to the efficient fin fans, and maybe cascade some cooling tower exhaust air to the fin fans, and probably more integrations after that. So a key insight is when you're thinking about integrating heat flows, think also about how to integrate and create new value from water flows, especially in a desert. Oh, one sad footnote. Our client loved our findings, but couldn't implement most of them because a partner firm in the consortium refused, even if our client paid the entire retrofit cost but took only its share of the savings. So the refusing partner would get more profit at no investment. Oops. Well, I'm confident none of you would make that mistake. Thank you very much.